Saccharide object is a born-again giant that has been losing dust in varying amounts since 1996. This study uses 6 Spitzer spectra obtained between April 2005 and October 2008 to look at changes in the type of dust and the amounts of dust produced. At the time, the carbon-rich photosphere was obscured by dust. It should also be noted that the object is surrounded by a 40 milliarc-second torus and a much larger planetary nebula, which presumably contains much older dust. Evans et al. 2020 first published these spectra from Spitzer. They noticed a weak absorption feature between 6 and 7 microns, which they assigned to some sort of carbonaceous material due to the carbon-rich atmosphere of Saccharide object. But I have noticed that over time these features have grown in depth. I'm particularly interested in a feature at near 6.9 microns, which is also seen in young stellar objects and molecular clouds. Usually this band is associated with methanol ice due to the presence of large amounts of water ice in these lines of sight. Once continua have been subtracted, it is much easier to see the growth in the features over time. The main part of the band can be matched by polycyclic aromatic hydrocarbons. And there is also space for another carbonaceous candidate, very large silicon carbide grains, which would be opaque in their main feature at around about 12.4 microns. However, these features do not add up to match the observations. Another absorption is required at about 6.9 microns. This is the feature which is similar to that observed in young stellar objects and molecular clouds. However, there is no water ice in Saccharide objects, so there can be no methanol. Without water ice, there can be no carbonates, because water is required to make them. There is also no carbonaceous candidate that I could find. The only candidate I could find was an oxygen-rich candidate. This is very large melalite grains. Melalite is a calcium and aluminium silicate, and this feature has also been suggested to be present in young stellar objects and molecular clouds by Bowey and Hofmeister 2005. At longer wavelengths, the very large grains will not be seen because they are opaque. I used the fits obtained in the near-infrared with polycyclic aromatic hydrocarbons to match the longer wavelength data. In order to fit the shape of the profile, it also needed diffuse medium silicates to add to the absorption. However, this did still not fit the feature properly. What was required was some optically thin silicon carbide emission from nanometer-sized grains. The modelled silicon carbide emission varied between epochs. It decreased at the beginning and then rapidly increased between the 21st and 30th of April 2008, and then continued to increase up to October 2008. At the same time, the amount of modelled interstellar silicate absorption decreased between October 2007 and October 2008. The decrease was subtle, but it was consistent across epochs. I have deduced variations in the silicon carbide emission component. I have also deduced an increase in the PAH abundance during the entire observation period. There might also be large silicon carbide grains with meteoritic sizes that cannot really be easily detected by any other method other than overtones. An estimate of the coal dust produced by this star can also be made, but is not presented in detail in this work. The apparent conversion rate of submicron-sized silicates into 10-micron-sized silicates matches the proportion of melolite-bearing silicate grains in meteorites. I am guessing that this is only one part of the silicates that have coagulated. I would conclude that Saccharase object should be monitored by JWST. The complete analysis is given in Bowey 2021.